Welcome to the deep dive. Today we're diving into inferential statistics.
That's right.
Your sources are often full of data, numbers, research, and inferential stats is really about, well, how we take that specific info and make broader claims,
Exactly. It's about understanding the whole picture, the population, when you've only actually seen a part, the sample.
which is most of the time, right? We rarely get data on everyone.
Almost never. So descriptive stats tells you about your sample, but inferential stats, that's the toolkit for saying something meaningful about the bigger group.
It tackles that core challenge, learning about the whole from just a piece. Super important in, like, business decision-making, I imagine.
Oh, absolutely. You're always trying to figure out the market, your customers, based on surveys or sales data, which are just samples.
Okay, so today we'll kind of unpack some key ideas. Random variables, distributions like binomial and normal, sampling, the central limit theorem.
And estimation, point, and interval estimates, all the good stuff.
Let's start with the basics then. Random variables. Your sources had that university exam example.
Right. The number of students who pass, it's a variable, it takes a numerical value, but the outcome is based on chance, and each possible number of students passing has some probability attached.
And there's a difference between discrete and continuous ones.
Yeah, big difference in how we handle them. Think insurance claims, you can count the number of claims, 0, 1, 2, 3. Finite or countably infinite values, that's discrete.
Okay.
But then think about the volume of soda in a bottle. It could be 500 milliliters or 500.1 or 500.001. You can't list all the possibilities between, say, 499 and 501 milliliter. It's a continuous range.
Makes sense. And these variables have a probability distribution.
Yeah, basically a description of all the possible values the variable can take and how likely each one is. You mentioned probability mass functions for discrete.
And probability density functions for continuous. That employee sales tracking example showed this well, didn't it? Linking sales numbers to frequency.
Exactly.
Yeah.
It gives you the shape of the data's likelihood.
So let's talk specific distributions that pop up a lot. Bernoulli.
Ah, the simplest one. Just one trial, two outcomes. Success or failure. Like, is this manufactured part defective, yes or no? Or a medical test result, positive or negative?
Got it. And binomial builds on that?
Precisely. It's like running multiple independent Bernoulli trials. So you survey 100 adults, how many you post on TikTok. You're counting the success as people who say yes.
But there are rules, right? Assumptions.
Yeah, you need a fixed number of trials. The trials have to be independent, only two outcomes for each. And the probability of success has to stay the same for every trial.
Although you mentioned the rain example, sometimes those assumptions get bent a little in practice.
Well, yeah. For practical purposes, sometimes you relax them slightly, like assuming daily rain chances are independent, even if technically there's some weather pattern dependency. You just have to be aware of it.
Okay. What about the uniform distribution?
That's where every outcome is equally likely. Think rolling a standard 6-sided die, each face, 1 through 6, has a 16 chance.
Can that be continuous too?
Sure, like if a machine generates a random number between 0 and 1, any value in that range is equally likely. Or maybe temperature fluctuating equally within a specific band.
All right, but the big one, the one everyone's heard of, is the normal distribution.
Ah, the bell curve. It's just so common. Symmetrical, defined by its mean, the center, and its standard deviation, the spread.
Why is it so normal? Why does it appear everywhere?
It pops up naturally in tons of places. Human height, weight, IQ scores, measurement errors in science, industrial processes. Lots of phenomena tend to cluster around an average with symmetrical variation.
And it has that neat property, the empirical rule.
Yes. Roughly 68% of the data falls within one standard deviation of the mean, about 95% within 2, and almost all, 99.7% within 3.
That food delivery time example in the sources illustrated that really well. Most deliveries cluster around the average time. Fewer are really fast or really slow.
Exactly. And we can use z-scores to standardize any normal distribution, basically converting values into how many standard deviations they are away from the mean. Makes comparing different data sets easier.
Okay, so we have these tools, these distributions. How do we connect back to the sample versus population problem?
Right, because we usually only have the sample, so we need good ways to sample. Simple random sampling is a key one. Every single item or person in the population has an equal chance of being picked.
Fair enough.
Yeah.
And then there's the sampling distribution.
Yeah, this is a bit mind-bending at first. Imagine you didn't just take one sample. Imagine you took hundreds or thousands of random samples from the same population and calculated the mean for each sample.
Okay.
The distribution of all those sample means is the sampling distribution of the mean.
And this leads us to the really powerful idea.
The central limit theorem, CLT. It's central.
What's the gist?
The amazing thing is, even if your original population data isn't normally distributed, maybe it's skewed or weirdly shaped, the sampling distribution of the sample mean will look more and more like a normal distribution as your sample size gets bigger.
Wow. Even if the source isn't normal.
Yeah, provided you're doing random independent sampling. Usually, a sample size of 30 or more is considered large enough for the CLT to kick in reasonably well.
And that's huge, because it means we can use the properties of the normal distribution for inference, even if we don't know the population shape. Larger samples help too.
Definitely. Larger sample sizes mean the sampling distribution gets narrower, more tightly clustered around the true population mean. So your sample mean is likely to be a better estimate.
Which brings us neatly to estimation, using the sample to guess about the population.
Exactly. We're estimating population parameters like the population mean or proportion using our sample statistics.
Two types, point and interval.
Right. Point estimation is simple. It's a single number, your best guess. So you use the sample mean as your point estimate for the population mean. Easy.
But maybe not super informative about uncertainty.
Correct. That's where interval estimation comes in. We create a range of values called a confidence interval.
Like, we're 95% confident the true population mean lies between X and Y.
Precisely. It gives you a range plus a level of confidence. Now, that 95% is a bit tricky to interpret sometimes.
How so?
It doesn't mean there's a 95% probability that the true population parameter is within the specific interval you calculated.
Oh.
It means if you were to repeat the entire sampling and interval calculation process many, many times, 95% of the intervals you construct would actually contain the true unknown population parameter.
Ah, okay. It's about the long-run reliability of the method, not the certainty of one specific interval.
You got it. And you wouldn't want a 100% confidence interval, right?
And not. Sounds great.
Because to be 100% sure, your interval would probably have to be incredibly wide, maybe like the mean is between minus infinity and plus infinity. Not very useful information.
Fair point. So, okay, let's wrap this deep dive up. Inferential statistics is basically our bridge from limited sample data to broader conclusions about populations.
Yeah, using tools like probability distributions, understanding sampling methods.
And leveraging that powerhouse, the central limit theorem, lets us make these estimations.
And we can even state how confident we are in those estimations using confidence intervals.
It really gives us a framework for dealing with uncertainty.
It does, which leads to maybe a final thought for you, the listener. How can understanding these ideas help you evaluate the information you encounter every day?
Good question.
When you see a claim, a statistic, a generalization, maybe based on a poll or a study, think about the sample. Think about the inference being made. What assumptions are underneath it all? Knowing a bit about this stuff lets you be a more critical consumer of information, making better judgments even when you don't have all the facts.